Okay, so welcome to Fundamentals of Calculus, Math 19. So today we're going to go over the syllabus probably. I'll tell you a little bit about me, what the course is going to be like, and we'll get started. So, yeah, come on. So, yeah, this is Math 19. I'm Andy Reagan. I'm a PhD student in math here. I've been here for 4.5 years. And I'm studying applied math, doing weather prediction work. Maybe I'll tell you about some of it at some point. Just going to go through this and make sure you guys know what's going on with all the details. So. Okay, so my office is in Farrell Hall. I don't know if you guys know where that is. It's over in Trinity campus. It's like in the back. But yeah, that's that. If you send me an email, feel free to email me with any questions. Just put Math 19 in the subject so I kind of can collect it. You know what's going on. I'm going to have 2 office hours Wednesday at 1. And I have a little 50-pound black lab named Finn. And he'll be there on Wednesdays, so if you don't like dogs, don't come Wednesday. But and Thursday I'll have an office hour at noon. And there's, I don't know if you guys know about the math help sessions. There's a lot of resources on campus for help, etc. And one of them is 5 to 7 p.m. Tuesday through Thursday. There's a help session you can go to somewhere on campus. On Thursdays it's in Calkin. And I'll be there for an hour on Thursday nights as well, if you have any specific questions about the class. Okay, so there's a course webpage. This is section E, as you guys may know. So you guys have a webpage out on GitHub. It's really just got a link to the syllabus. Lose it, and it's got a link to the My Math Lab sign-in and some instructions on like how to log into My Math Lab. We'll be using that for homework. So. Okay, this class, you guys have figured out, is at 8:30? Oh, okay, great. The book, Calculus with Applications, it's this book right here. I hope most of you guys have it. Does anyone not have it? Okay, so I guess I'll forget it. Okay, so, let's go. Good. So, one thing to know is you need to get the book with the My Math Lab subscription, so there's like a code that comes in it that allows you to sign up for the online part. So if you buy a used copy, make sure it has that. You probably need to buy a new one. You can buy just the supplement part at the bookstore or online, and that includes an ebook too. So you can do just that if you want to. But you do need the supplement for access to the homework. Okay, a little bit about the course. So yeah, this is the first semester calculus. There's a second course, Math 20, which is Fundamentals of Calculus 2, that goes into integration. We might go into that a little bit. So yeah, we're going to study differential calculus, functions, limits, continuity, rates of change, derivative applications. Yeah, we're going to do modeling. We're going to try to do some modeling of real world situations. Hopefully some stuff that is useful to you guys. So yeah, graphically, numerically. Okay, you guys can read the rest of this. It's good to have a graphing calculator. It says, I think here, yeah, it's highly recommended. No, I think, yeah, required for you to have a calculator. You don't need one, but you probably want one. You won't need it at any point in the semester, really. But if you're comfortable with it, you can definitely have one. So, yeah. Graphing calculators are good, but yeah, you don't want to. You can cheat a little bit with them, so you know, you can do like maxes and stuff. But so you're gonna have to show your work at some point. So. Even if you do use a graphing calculator, it can solve some of the problems. But I'm just if I ask you to show your work, you need to actually do the math to show me that you understand it. No. Okay, great. So for grading, it's four sections. The online homework is 10%. The course ID is down here. Which is my last name and some number. So when you sign up online, this is with the instructions on the online webpage, and when you sign up for My Math Lab, you're going to want to find this course. So generally, I put up a homework after every class. It'll take 30, 45 minutes to complete. I think you have unlimited tries. You might have like 5 tries on each question. Yeah?
I get to fever.
Oh yeah, you didn't go. Yeah, I'm sorry. And someone else came after too. Yeah, sorry. Okay. Great. Okay. My Math Lab. If you have any questions about it, I'm new to it as well. So I'll be trying to figure it out. first homework teaches you guys like 2 hours because if you click too many problems, then let me know. So. Okay, class quizzes, 20%. Yeah, so every Thursday, this is a Tuesday, Thursday class, every Thursday at the end of class, we're gonna have like a 15-minute quiz. It's gonna be really simple. If you come to class and pay attention, it's just gonna be exactly like one of the problems on the board, probably different numbers. But just kind of to show that you have grabbed that concept. I'll drop the lowest 2. Great. Okay, tests. There's going to be 2 tests and closed notebook. Also, the quiz is closed notebook. You can see, if you turn you can see when the exams are. So we're going to have 5 weeks of class, then a review and an exam. Again, 5 weeks of class, review, exam, and then break. And then really just 1 more week of class before the final. Final exam, yeah, will be cumulative. It's 30% of your grade. Close notebook. Okay, great. And for grades, you guys can read this. Okay, expectations. You guys can read all this stuff. Okay, yeah, the help sessions, there's a link for them down here, which is pretty useful if you guys want homework and stuff. Generally, the homework, I'm going to assign it immediately after class, and then you guys will have like a week to do it, maybe 3 or 4 days. It shouldn't be too bad. And okay, on the back, yeah, so this is like day by day, what to expect. Quiz every Thursday. And in addition to that, what else do we have? Yeah, the final exam. So we're section E. So the final exam is going to be at 7:30 a.m. on the 14th. Okay, great. And I think somewhere in here it says to turn your phones off, which I haven't done yet. Okay, great.
You said the 14th and 15th because they're both section E.
Oh, did I? Okay, yeah, the first one.
Oh,
the second one is going to be section F. Yeah, okay. Good catch. Yeah, and you can find this online. There's like some huge list of when all the finals are. So I should probably show up for that one. Okay, great. Do you guys have any questions about syllabus? Is there anything you weren't sure was going to be in the class, or? Okay, great. I'm going to ask you guys some questions. Start. So, like, how many of you guys have had calculus in high school or before? Okay, so like half of you guys. So that's great. A lot of this at the beginning is going to be pretty easy. So try to stay awake. And yeah, we're going to start with section 1. Let's make sure that we've got everything else. Okay. So syllabus, course webpage. Yeah. Okay, and yeah, I guess one final note is to make sure that you guys are in the right math class. So there are 2 calculus sequences. There's 19 and 20, which are for people who aren't in math or aren't going into like engineering. And then there's the 20 and 21, which are, or it's 21 and 22. There's this 19 and 20 and then 21 and 22. So the 21 and 22 are like more rigorous, quite a bit harder. They cover the same things but go into more depth. If you are going to be in engineering, that's probably the class you want to be in math. But otherwise, this is fine. Probably satisfying your requirement. Great, so just make sure. Double check that you shouldn't be at math 21. And great, so we're just going to go ahead and get started. I have a couple examples I was going to show you guys. So how many of you guys are in business students in the business school in total? Okay, so like 6 or 7. Okay, so one motivating example, you think, okay, calculus, I'm in business, it's not very useful, I can take derivatives. Okay, so I'm going to show you guys an equation. It's called the Black-Scholes equation. Okay, so I'm going to write this out. It's not going to look like much, but you don't need to write this. Black-Scholes equation. this is the Black-Scholes partial differential equation, right? Probably doesn't look like much, but what we're going to do in this class is we're going to study derivatives, right? So these are the derivative terms. They're more advanced. They're with respect to different variables and such. But the interesting part about the equation is Black and Scholes got a Nobel Prize for solving this equation because what this equation describes is options pricing in the stock market. So if you so V is the price of the option and S is the price of the stock. Some of these other things are parameters about the market. And if you can solve this, you can actually figure out a no-risk cost for pricing an option in the market. So they found this out, solved it. I think they published it. They probably could have went and made lots of money first. But yeah, so you can describe markets this way. Really interesting. Okay, there is some calculus in economics. That was kind of the goal. Okay, and how many of you guys are in biology? In general? Okay, so a lot of you guys are biology related. Okay, so I looked up some equations that are calculus related that are in biology. So a lot of people in biology do like mathematical modeling of like species. You get the predator-prey models, and also within cells you can model like how different molecules are interacting, and even on a population level, like how disease spreads and stuff like that. And so there's a set of equations called the Black-Scholes equations, which describe this evolution. And I'm going to show you the third calculus equation. So, okay, these are the competitive Black-Scholes equations. So, dx1. All right, so this is one species of the equation. I'm not going to write more than one, but you can use as many as you want. So this this just describes the predator-prey dynamic. So x1 is like one species, or you can also use this to model molecules and everything like this. And to solve this kind of equation, this kind of derivative equation, you can use calculus. Okay, so that's our grand motivation, solving the Black-Scholes and the competitive Black-Scholes equations. And people do solve these generally on computers, numerically. There's also some exact solutions known. Okay, great. So now we're going to start with section 1.1. So we're going to go through chapter 4 into exam 1. So we're going to start section 1.1. Okay, so section 1.1 is on page 2 if you brought your book. And it is slopes and equations of lines. So here we go. Great. Okay. Section 1.1. Page 2, and we're going to start with just kind of an example line here. So here's just an example line, right? Okay, and so this is going to be so this point here is at 0, 1, and this point here is at 2, 1.5. So this is, an example where, you could have value of a company or a startup or something like that, and over time, right? So year 1, valuation, $1 million, right? -1, 0. And year 1, you'd have the value 1, and then 0.25. Right, year 2 saw valuation went up to 1.5 million. Right, so we want to be able to describe and model this evolution. So we're going to write down the definition of the slope. So definition. Slope of a line so we're going to find the slope as m. You're going to see it defined as m anywhere, kind of an arbitrary choice of variable. And the slope is the change in y over the change in x. And sometimes we write this shorthandedly as delta y over delta x. This is lowercase great delta. And this is the uppercase great delta, which is just the difference in y over the difference in x. Great, so as an example, we can go figure out the slope on this line. We can use any of the points we want, really. But let's pick this end point as our second point, and this first the starting point as our first point. So we have, x1, y1, x2, y2. So we're going to say m equals delta x. Actually, the other way around, right? M equals delta y over delta x, which is going to be y1 or y2, 1.5 minus y1, so it's 1.5 minus 1 over 2 minus 0 from x. And this is going to be 2.5, 2, which gives us a slope of 1.25. Right? Does anyone have any questions about what the slope is? Did I make that clear? Great. Okay, so we're going to define a couple other things that are going to help us describe this evolution. So the equations of a line. So we're going to look at two different ways to write the equation of a line. So equations of a line, we're going to define two different ways to do this. So the first one is slope-intercept form. Slope-intercept form, where we have y equals mx plus b, where m is, of course, the slope, and b is the y-intercept. Right, so here, x is our independent variable, y is our dependent variable. Okay, and the other way to write a line we're going to look at is point-slope form. So and this is going to be y minus y1 equals m x minus x1. Right, and we'll write down both of these using the example. So this one is, of course, more useful when you have the slope and the y-intercept. Just write down. If you don't have the y-intercept, or it's just not as easy, you can use the point-slope form. And you just need a point, x1, y1, and the slope. Right? They're the same thing. So they're, if you were to write these down for the same line, these equations will be the same equation because you're describing the same line. So if we go ahead and write down the slope-intercept form for the first equation, or for that line we saw here, the y-intercept here is -1. So we can say y equals, we already found the slope, 1.25 x plus -1. Right. So this is slope-intercept form. Right. Okay, and if we want to write the point-slope form for this, we have y. Someone want to pick a point? What would y1 be?
-1.
Okay, so -1. Great. So use y minus -1, and in that case, your x1 point would be what? 0? Yeah. X minus 0. So this equation becomes y plus 1 equals mx, right? And if we were to, yeah, okay, I didn't put the slope in. So the slope we know is 1.25. 1.25x. And if we go ahead and put that minus out, we get 1.25x minus 1. And so you guys should be able to see that these are actually the same equation. This one subtract 1 from both sides, and this one add 1 to both sides. We have the same equation describing that line. Great. Does anyone have any questions on either of these? Have you guys mostly seen this before? Okay, right, so important. Great. Okay, they're the same. Great. Okay, there's 2 other types of lines that we're going to write down. You guys good with this stuff? Okay. So other types of lines. So horizontal and vertical. So a horizontal line, does anyone want to venture a guess what an equation of a horizontal line would look like?
Y equals 1.
Yeah, so y equals 1 is a perfect horizontal line, right? Y equals 1, it's just going to go flat across. And so I'm going to say y can equal k, where k is any constant. Okay. So good choice of one. Okay, and similarly, vertical line, x equals k. So x equals k, yeah. Okay, and briefly, the slope of each of these is going to be fixed, right? So the slope of a horizontal line is what? 0. Okay, yeah, and of course you could plug it into the equation we had, where the y2 minus y1 is always going to be 0 because y is not changing, right? So this would just be, we do this one. This is just m equals y2, which is always k, minus y1, which is still always k, over any x points you choose. So you can choose x equals 2 and x equals 0, like we did, but this flat line is always going to have slope k, or slope 0. And the vertical line, x equals k. So the slope for a vertical line, we're going to say, is undefined, right? So, write something. Okay. So if we have k here and k here, the line, this is the line y equals k, y, x. This is the line y equals k, and this is the line x equals k, because of course x always equals k. And yeah, like we just did, the slope from the point here, we just did the slope from 2 to 0 on y equals k, right? And if we were to do that with x, so if we picked, the point here, say k is something like 2, we're going to get, for the vertical line, m equals, well, here for y, 2 minus 0, right, over k minus k, which is, of course, 2 over 0. which is on the line. Can't divide by 0. Great, I think that's it for lines. Okay, let's see. Okay, no, there's two more definitions. Okay, so we're going to talk about 2 more definitions of lines, and these are parallel and perpendicular lines. And so you're just going to use the slope. So definition, 1R, 2 L's, right? They are parallel and perpendicular. So 2 lines are parallel. If they have the same slope. Okay. Great. And 2 lines are perpendicular. Perpendicular. If they have inverse, well, let's say negative reciprocal slope. Okay, so the negative reciprocal just means that if you multiply the 2 slopes, it's going to equal -1. So negative just means they're negative of each other, and reciprocal means one's 1 over the other. Okay, so if you multiply them, they're going to cancel the 1, divided by the same number. And they're negative of each other, so if you multiply slopes, you get -1. Great. Can you guys read my handwriting? Is this okay? I try to record it. It's fine. Okay, great. Great, and so of course, if you're ever curious about any of the definitions, they're also right in the book. So I think the book says for perpendicular lines, yeah, so 2 lines are perpendicular if and only if the product of their slopes is -1. Right, and of course the other example is these lines are perpendicular. But their slopes are, undefined. Or if one is vertical and the other is horizontal. Okay. Great. I think we're going to do a couple examples of graphing lines. Okay, so let's do that. Lines. -2, -5, -6.5. Okay, so let's go ahead and graph this. Chalk. Okay, so x, y, so we're just going to go ahead and plot each point. So here you have the ordered pair 0, 2, 0, -2. So we're going to go ahead to x equals 0, y equals -2. We have that point. X equals 2, so this point is 0, -2. We're going to go over 2 -5, so we're going to go 2 on x and then -5 on y. This point is going to be 2 -5, and then we're going to go over to 3 and -6.5. And this is going to be 3 -6.5. that's the graph of this line with the points. Pretty easy to do if you have the points. We're also going to do it, and if we're given the equation of a line, right? So y equals 10x minus 5. There's a handful of ways to do it from the equations. It's 10x minus 5. So the slope here is what? 10. Okay, and y-intercept? Negative 5. Okay, so from that, we know the y-intercept is negative 5, right? So we know 0, negative 5, we know that point. And we could find out any other point we want by just plugging in an x value, right? So if we want to know where this line is when x is 1, we can plug that in. So we're going to get, so this is at x equals 1, y equals 10 times 1 minus 5, 10 minus 5, which equals 5, right? So now we have a point, 1, 5. And we can go ahead and put that on. Here, 1. And so we have this steep line. Of course, you could just look at it too and say, okay, well, I've got a point here. I know the slope is 10, so every 1x I go up 10, because that's the slope. And just put the point here, right? That's here we go, and I think one more. Do one more example. Okay, so we'll do one from the point slope form. So y minus 1 equals minus 3 x plus 4. Great. All right, we don't have the y-intercept. So how do you guys think we should start? What do we know about this line?
You know the slope.
We do know the slope. Great, yeah. So we know the slope is minus 3, which is going to tell us it's going to be kind of steep going down like that, right? So if we wanted to get a point on this line to start drawing it, we can plug in a point. Of course, so we can plug in x equals 0 with the y point. Probably just the most straightforward way to do it. Or because this is in point slope form, that you have y minus y plus y minus y1 from the point slope form, and x minus x1 from the point slope form. So x1, y1 is a point. But it's minus, so it's a little tricky. So it's x minus x1. So x1 is actually minus 4, right? And y is 1. So we know this is a point because we can see that it's in point slope form. If you wanted to try that point, of course, we can plug in x equals minus 4. So if we do x equals minus 4, we plug that in, y minus 1 equals minus 3 minus 4 plus 4, which is of course 0 on this side. Is at 0, 3 times 0 is 0. So y minus 1 equals 0, so y equals 1. And we have the point, minus 4. Of course, you can see this too, because if you just put in minus 4, that whole side is going to go away. Great. So to plot this, we can go ahead and use this point. It's as good as any. So go over to minus 4, go up 1. Right, and we know the slope is minus 3. So we know for every x we go, we're going to go down 3. So we can go forward x, down 3. Or, of course, we can plug in x equals minus 3. Right, we're going to get y minus 1, minus 3 plus 4. Right, so y minus 1 equals minus 3 is going to be 1. Y minus 3 equals minus 3. So y equals minus 2, right, adding one to both sides. And so we have you know, y equals minus 2.
How's everything going? Good? Good.
And so we can go ahead, we have 2 points on the line. We can go ahead and draw that line. Okay. Do you guys have any questions about these? Okay. So we can draw the graphs. You could do it, of course, if it isn't in either of these forms by just plugging in points and going from kind of a table of points. It's kind of just a fallback way to do it. Great, so you'll have some homework questions like this. Okay, so that's section 1.1, equations and lines. Great. Go ahead and fix this. Okay, great. So we're going to jump right into section 1.2. What time is it? 9:07. We might finish chapter 1 today, guys. No one says anything. 1.2, linear functions and applications. This is on page 17. Okay. So the first thing, we're going to define a relationship F. So we're going to define the function itself. A relationship. Let's see. Relationship F. Function f is defined by y equals f of x is the notation. And of course, this could be a line in point slope form. This could also, yeah, so this is the y-intercept form. This could be a line in point slope form, of course, as well. And in that case, you generally want to solve for f of x. To write the equation as f of x. So we're going to say a relationship defined by this is a linear function. Great. What do we mean by linear, right? We just mean that the slope is constant. So because we have a constant m, it's going to be a straight line, and that's what we mean by linear. Something that's not linear would be something like quadratic. You know, you've got squares, the line is curving, something like that. Great, we can do a lot with linear functions to start. Okay, so I'm going to do the example 2 in the book, which is linear supply and demand. So we can, you know, we're going to be talking about watermelons. Okay, great. So if you're a manager of a grocery store and you're selling watermelons, you might notice that the price of the watermelons dictates how much people buy them. So if you raise the price, less people are going to buy them, and your supply will go up. Right? So you want to find the price, which, you know, the most people buy them, but you still have some in stock. Because if you gave them away, you'd be out. Okay, great. This is our example. So, example is linear supply and demand. It's example 2 in the book, if you want to look over it. So we have an equation for the price, P, which is going to be based on the demand, Q. So this is, price is the demand of Q, so the quantity Q. So price is a function of the demand. And we notice that we have a relationship that looks like 9 minus 0.75 Q. So we found that, you know, in the operation of our watermelon store, that this is how the price acts when we change the quantity, right? So if we want to go ahead and use this, we can let's find the quantity demanded for a price of 525. So if we set the price at 525, how many are going to be demanded? So the demand quantity is based on price. So price is 520. Well, you're all right. So this is going to be find quantity demanded for a price of 525, right? And because we have the price, right, we have an equation for the quantity, or the demand of quantity, we can just plug this in. So we have a price of 525, so we can write 525 equals d of q equals 9 minus 0.75q, and we can solve for q here. So we subtract 9 from both sides, and we're going to get minus 3.75 equals minus 0.75q, and if we divide by 0.75, we're going to get that q equals 5. Right, so if we set the price at 525, we're going to get a quantity demanded of 5. Right, I guess the only really new thing here is this notation. We're writing the demand as a function of q. Okay, and we're also going to have the supply relation. So what's that? So we're also going to observe the equation price is dependent upon the supply, like 0.75q. Right? Okay, so let's do the same thing. Let's find the quantity. Find the quantity demanded. Not the quantity demanded, right? The quantity supplied. Supplied at a price of 525. Okay, so yeah, go ahead.
Sorry, I think I missed where the 0.75 comes from.
Okay.
You just gave us.
Yeah, so this equation is given, right? You're given this, and you're also given this.
Oh, okay.
Yeah.
At the bottom of the other side of the board,
Yeah.
is that 325 or 375?
It's 375. It's 525 minus 9, right? Yeah. Yeah, okay. I'm getting a little sloppy. It's 370. Great. Okay, so we have, that's the price equation, that's the demand equation, this is the supply equation. We're given both, of course. So we're going to want to find the quantity supplied when the price is 525. So similarly, we know P equals 5.25, so we're going to set this equal to S of Q, which equals 0.75Q. Right, we'll go ahead and divide both sides by 0.75, right? And so Q equals what?
7.
Great. So at that price of 525, we would have 5 demand. How many? We had 5 demanded, right? And we would have 7 supplied. So our price in that case would have been, we had less demand. Our price would have been too high, right? So if we want supply to equal the demand, we can go ahead and set these equations equal. So this is going to be called the equilibrium price. So type C, find the equilibrium price. Okay. And so to do that, we'll go ahead and set these equations equal. But first, we can think about this graphically. Right? So if we're to plot the demand curve, of course, price has to be, or quantity has to be Q, P. So quantity has to be positive. So it really only makes sense to be over here. Plot it over there, but it only really makes sense over here. So for demand, how do you guys think we should plot this? Should we just plug in some points? Yeah. Okay. We know the y. We know it's in slope-intercept form, right? So the y-intercept here is what?
9.
9. Okay. Great. Great. So for d of q, we have that the y-intercept is 9. So we're plotting the first one. And if we wanted to get one more point to be able to plot this, we already have it, really. Okay, because we plugged in 525 for the price, and we got that the demand was 5. Right, so we have, it's as if we plugged in 5 here, right? We get 525 out. So we have the intercept, and we can go ahead and plot one other point. So quantity 5, the price is 525. So it's like here. Right, so as we increase the price, the quantity demanded is going down. And so if we want to go ahead and plot this one, the supply at any given price. So we know that the y-intercept here is what? 0. Okay, good. So we can start here, and we already did one point here too, so we know Q equals 7 for 525 price. So 525 price here, we would have Q equals 7. So this one here is demand, supply. Right, and so you see at some point, at some value of Q, supply equals demand. Right, and to find this point, we can set these equations equal. We want to know where D of Q equals S of Q, and then we can solve for that. I will say that this example is a little weird because you have the independent variable on the bottom, really, because price is what you set. Right, so price here is more like the independent variable. You set price, and then you get a demand or a supply based on that price. So if you set the price to 0, you have a lot of demand and you have no supply. It's gone. But if you set the price a little bit higher, you have a little more in stock and a little bit more, or a little bit less demand. So as you increase price, demand goes down. And as you decrease price, supply goes down. Right. So that is a little weird if you're trying to like think about how this makes sense. Here, the independent and dependent variables are kind of flipped, and the book says this is because this is how economists do it. So makes me question their methods. But okay, we can go ahead and solve for this. So we'll just do it right here. So we want to know where D of Q equals S of Q. Right, so we know D of Q is 9 minus 0.75 Q, and S of Q 0.75 Q. Right, we just want to get all the Q's on the same side, so we can add 0.75 Q to both sides. We're going to get 9 equals 1.5 Q. Then we can go ahead and divide by 1.5. And we can see that 6 equals Q. So our equilibrium supply is 6. Right, so we could plug into either of the equations. Actually, I think I did a pretty good job plugging it. So this actually looks like 6. We can go ahead and find our price from either equation at a quantity of 6. So it's pretty easy from the supply. At a quantity of 6, right, the price would be what? 0.75 times 6 is 4.5. Right? So the equilibrium price is 4.5. You guys will have an example like this. Do you have any questions about this? Yeah. Okay. If in doubt, you can always plot it, and you kind of want to make sure that your answer makes sense. Is always a good thing to do. So like, you ended up with 6. Okay, well we graphed it. Looks kind of right. It's not going to be minus 10. Like that doesn't make sense. I am going to put my notes up online, which are just notes from the book that I'm using to write on the board. They're not going to be super helpful, but you don't need to write everything down because things that I write down I've already written down here. If you don't want to, so but they're not as clear as this. So. Okay, we're going to do one more example of finding the equation of a line. So. So we're going to write down the equation of a line for something you guys are probably very familiar with. So, okay, on this axis, we're going to write the Fahrenheit temperature, and on this axis, we're going to write the Celsius temperature. Right, so when it's 0 degrees Celsius, that's freezing point, right, of water. What is that in Fahrenheit? 32, right? So we have the point Fahrenheit to Celsius. Celsius is 0, we have 32 Fahrenheit. Okay, and boiling point at 100 Celsius is what in Fahrenheit? 212, yeah. And body temperature, 37 degrees Celsius, is what in Fahrenheit?
98.6.
Yeah, right. I should have done it the other way. I think it's a little bit harder. 37. Okay. So we can go ahead and plot this. We really only need the first 2 points. So if Celsius equals 0, we have Fahrenheit equals 32. So this point is 0, 32. Right? And at Celsius of 100, we have Fahrenheit of 212. So 100, Fahrenheit 212, 212, 100. So this is a really crooked line. Okay. At this point, right. So we want to find the linear relationship described by this line. Right. So we have 2 points. Right. So the easiest thing here might be to do slope-intercept form, or the point slope form, or we also have the y-intercept, so we could do the slope-intercept form. But in both cases, we're going to need a slope, right? So slope m, we're going to take delta y over delta x, and this is going to be y2. So our second y point is what here? 212. And the first one is 32, yeah. Okay, and in x, x2 is 100, and x1 is 0. Okay. So this is going to be 180 over 100, which is 9/5, right? Great, so that's the slope. We have a slope of 9/5. So if we want to write down the linear relationship, right? So Fahrenheit we can do it with let's do it with both forms. So the slope-intercept form, we can write that Fahrenheit equals 9/5 Celsius, right, plus the y-intercept, which is 32. So if you want to convert. We can also do it with the slope-intercept form, so this one is good. Where if we use like the first point, Fahrenheit minus that point, minus 32, equals the slope, Celsius minus that Celsius point is 0, and hopefully you guys can see that these are the same line, right? These are the same equations. Okay, great. That's really all I have today. Sections 1 and 1.2. So that's it for chapter 1. That's all we're going to do. So if you guys have any questions, feel free to come up and ask me. But other than that, have a good second day of class.